My name is Matthew Hall, and this is Lab 3, which is the magnetic field of a bar magnet. The purpose of this lab is to measure the distance dependence of a magnetic field due to a bar magnet. And specifically, we're going to use experimental values, and we're comparing them to computational values using the Biot-Savart law produced on GlowScript. And we're going to find the magnitudes in both on-axis directions and off-axis directions. Some of the main principles we're going to end up using is the fact that the Earth produces a magnetic field. In the process of setting up the experiment, we have to ensure that the magnetic field produced by the bar magnet is in line with the Earth. We're also going to show that distance is related to magnetic fields. We're using the Biot-Savart law, which is seen on the bottom of the page. We're going to use the magnetic dipole equation and the magnitude of a bar magnet. The middle of the three equations on the bottom of the page is going to be implemented into a GlowScript code in order to calculate the computational values. Part of the lab setup is utilizing a bar magnet and a magnetic field app. And what it's going to show us the X, Y, and Z components of a specific bar magnet. Part of the procedure is to, number one, find the position of the magnetometer chip. And this is going to be aligned with the Earth's magnetic field to ensure there's no indifference in the values. Additionally, we're going to record values for multiple distances from 20 to 220 millimeters, and we're going to conduct 3 different trials and find the average and graph them. By doing so, we can calculate distance dependence and the magnetic dipole moment. On top of that, we're going to locate a distance of 100 microteslas. And with that, we're going to once again find components of a magnetic field at that 45-degree angle. And so here's some of the results from my experiment. As seen in the graph that's produced from the values, we get a distance dependent of negative 0.29. On top of that, you can calculate the magnetic moment of 7.32. And all you can see from this example, from this graphic, is the fact that we conduct 3 different trials and we are able to calculate the magnetic field from each of those trials. And by finding the average, you can find how distance is related to magnetic field. And so here's some parts of the computational model. On the left side, you can see how we created arrows and axes in order to show the magnetic field both perpendicular to the bar magnet and parallel to the bar magnet. On the right side, you can see how we implemented the same magnetic field equation from before. And at the end of the code, we use the perpendicular distance, the point at which we find 100 microteslas, and we use that to calculate our magnetic field. And here's some of the results. You can see the arrows that were produced. It shows the directions both on axis and off axis, and some of the values produced by that, some are negative and some are positive respectively. And additionally, we find that we can find the distance of about 0.366, which is slightly different than the off axis produced experimentally, which is about 0.258. And a lot of the difference is due to the presence of additional magnetic fields that were uncontrolled, and there's a lot of sources for magnetic field strength that can't be accounted for when conducting an experiment like this. And so some of the final questions that we can ask ourselves is, what happens if you don't compensate for magnetic north, specifically of the Earth? And the readings will definitely be inaccurate. You must account for it because that is a controlled magnetic field, and if you don't do so, then the differences in values that we see between the experimental value and the computational model will be much greater. Also, what happens if you stick two identical magnets together? We would just see a large increase in the strength of the magnetic field. The measurements will differ slightly, but that's just because we're now increasing the strength altogether.